Okay, welcome to Math 331, the little questions. This is lecture 4. And so what I want to do today is a little bit based on what you want to talk about, but I want to discuss, coding efficiency, recurrences, and then probably segue into inequalities. If people want to talk a little bit about progress being made on the tiling problem, happy to do that. So we're going to start doing project Euler problems. Many of these problems are absolutely trivial from a theoretical perspective. From a implementation perspective, they get extremely hard extremely quickly. Where there's a lot of things where I can give you an algorithm that will work, but the universe will die a heat death, before the algorithm makes any significant progress. So you have to find good ways to attack things. So this is something that came up in some work I was doing with some high school students, where we needed to understand things about triangle numbers. And so I think we've talked about triangle numbers before. There's lots of ways to draw them. I'll draw them this way, 1, and then 2, and then 3, and then 4, and so on. So Tn is just 1 plus 2 plus ... plus n, and it's a nice exercise that this is n plus 1 over 2. There's many ways to see this. We've talked about proving formulas like this by induction. One nice way that's done is you write it backwards. So one proof is if I write Tn as 1 plus 2 plus ... plus n, and I write it again and I write it backwards now, n minus 1 plus ... plus 1, then you see that twice Tn equals, each one is going to be n plus 1, and we have this n times. So this is going to just be n times n plus 1 over 2 for Tn. So this is often attributed to Gauss when he was in kindergarten, and just the teacher was just having one of those days. And we've all had those days when you just don't want to deal with people. No, I mean, I would never, of course, have them in a situation like this. Of course, I love this class. But in other situations where you just want people to go away, so you give them a task to just get them out of your hair for a while. And so the teacher allegedly said, add up the numbers from 1 to 100. Expecting that, these are 5-year-olds, this will occupy them for a while. And then Gauss immediately raises his hand, according to this, says, 5,050. And the reason is, Gauss noticed that you can just pair them like this, and now it's just going to be 100 times 101 over 2. And that's a problem we can solve very quickly in our heads. So the question is, when are triangle numbers perfect squares? And it turns out that that has implications for trying to prove certain numbers are irrational. Square roots of certain numbers are irrational. So if a triangle number is a perfect square, it's not going to have an irrational square root. And the first triangle number that's a perfect square is 8, is T8. So that's going to be 8 times 9 over 2, that's 36. Are there infinitely many triangle numbers that are perfect squares? If so, that's the first question. Are there infinitely many? The next question is, can you find them? Can you find at least one of them? Can you do something constructive? And so here is a terrible code to check to see if triangle numbers are perfect squares. And it's called naive, because this is the naive thing you would do. Input some maximum value, and for 1 up to maximum in steps of size 1, just check the square root of the nth triangle number, and Mathematica has a function that will tell you if it's an integer. And if it is, it's true, and you print it out, and if it's not, you don't. And I had it look all the way up to, I think, 10 million. It took a little bit over 2 minutes on my laptop to do this. And you can get some sense as to how long would this program take as you go further and further and further. As the number gets bigger, is it going to be longer to find square roots? Any thoughts about how we could make this program a little bit more efficient? We all agree that this program will work. How could we make it more efficient in terms of finding triangle numbers?
I don't know if it's related, but I think it's increasing by roughly a factor of 6. Yeah.
Okay, so you think that maybe there's some pattern as to how far we have to go before we find the next one? So at least conjecturally, if that's true, we could actually skip a bunch of numbers and just pray for the best. It's not a proof, but that probably would work and that would speed things up, and then just investigate. Yeah, the question, of course, is there an explicit formula for these numbers? Turns out there is, and we'll talk about that in a moment as to which inputs have perfect squares. But we're trying to look at the number n times n plus 1 over 2. What can you tell me about n and n plus 1?
It's a pair of even and odd numbers.
It's a pair of even and odd numbers. One of them is even, one of them is odd, right? The triangle numbers are clearly integers. We're dividing by 2. So either 2 divides n or 2 divides n plus 1. If I want a number to be square, then all of the primes that divide have to divide it an even number of times, right? So when I'm looking at this, is it possible that a prime divides n and a prime divides n plus 1? Why not?
It's more primes too.
Okay.
And so if it divides in, as you said, it's not going to divide n plus 1.
Well, what about 3 or 5 or 7? Could maybe 7 divide n and n plus 1? Why not?
For that same reason.
What's the reason? You got to be very rigorous.
Is that like if it divides in, then it would need to be n plus whatever that prime value is next and divide it. Or to be the next multiple.
You're close, but I want something rigorous.
But the remainder is always going to be non-zero for at least one number. Because if n is divisible, then n plus 1, the remainder is 1.
Okay, good. So if p divides n, then it has a remainder of 0. So then if I increase n by 1, that should give me a remainder of 1. Another way of looking at it is if I divide two numbers, do I divide their difference? If I divide x and I divide y, do I divide x minus y?
Yeah, you do.
So if I divide n and I divide n plus 1, I have to divide their difference. What's the difference between n and n plus 1? 1. So n and n plus 1, they're relatively prime. So if I want this triangle number to be a perfect square, if n is even, then n over 2 must be a square and n plus 1 must be a square. Or if n is odd, then n plus 1 over 2 must be a square and n must be a square. So really what I'm trying to find which numbers are going to give me squares, I don't have to check all inputs n. Either n or n plus 1 has to be a perfect square. So this is a slightly more efficient code. And again, the slides will be posted online. What I'm going to do now is I'm going to just move in steps of 1, and I'll check both n and n plus 1 for being a square. And this is going to greatly cut down on how many things I need to check. So again, I've got to be a little bit careful because maybe n is odd or maybe n plus 1 is odd. That's why I have two cases. So in the first case, I'm going to let m be 2n minus 1 squared. And then I'm going to look at, that's always going to be an odd number, right? So I'm going to look at then, that is my number. That's going to be my n, and then my n plus 1 would be m plus 1. So if m is odd, m plus 1 is even. That's the one that has to be a multiple of 2. So I just check to see, is the square root of m plus 1 over 2 an integer? Or maybe it's the n plus 1 that is the even one. And so then it would be m minus 1 would be. So again, it's not that bad to just code this up. Instead of taking 2 minutes, it took 0.04 seconds to just do something like this. Theoretically, the first algorithm works beautifully. But there were so many calculations we were doing needlessly. There were so many numbers we were checking that had no chance of being a perfect square that we shouldn't bother checking them. So I was able to do a little bit of analysis and say, I don't need to look at all possible indices. It's enough to just look at some of them. So, oh, did I Oh, I didn't include it here. Oh, well. I will just note that there is something called the OEIS, the Online Encyclopedia for Integer Sequences. Okay, so later today, you should go to the OEIS and you should input the first couple of numbers. So the first couple of indices, let's see, I think we've got, say, 8, 49, 288, 1681, ... You can put that into the OEIS and it will tell you all the sequences it knows that starts with those numbers. And it will tell you everything it knows about them. For some of them, it'll say, here's an explicit formula for the nth term of the sequence. Here are relationships between the terms. Here are some reference articles about them. It's an absolutely wonderful site.
That's awesome.
If you're trying to prove something by induction, it helps to know what to prove. And the OEIS will tell you, here is a conjectured formula. And it's like, I don't know that my sequence actually has these properties, but I know the first couple of terms, and now you're telling me it might be this. Sometimes you might have more than one sequence that fits. What should you do if you have that situation? Calculate more terms. And hopefully, eventually, you get to the point where there's only one sequence that still has a match with what you have. So again, strongly urge you to go to the OEIS, plug in various things. If you just plug in some random integers, there's a good chance it'll find something. But it's a wonderful website. Right. So I think the fourth project Euler problem is the first one that gets really interesting. I wanted to just talk a little bit out loud about the first one, finding the sum of multiples of 3 or 5 below 1,000. Okay, I want someone to give me a bad way to do this problem. Perfect. So the first way is march from 1 to 1,000, adding the number if a multiple of 3 or 5. Perfect. What's bad about this approach? You're checking every single number, and then the runtime is going to grow with the upper bound. If I ask you to just do this for the first 1,000 numbers, is this a big deal? 10,000, a billion. So how big is a billion? 10 to the 9. Do you think your computer can do a billion? I just did, on the previous page, I just did 10 million. That took about 2 million, but 2 million steps, so I was looking for square roots. If we're just doing counting, do you think you can get up to a billion? Yeah. You know, it may take you a couple of minutes to a couple of hours, depending on your computer, but a billion is not too bad. If I start getting to a quadrillion or a googolplex, you're not going to be able to do this with this method. So this method will break down. But if it's something very targeted, 1,000, this will work. Can someone give me a better method? Yes.
Cycling through all the, or go through the multiples of then do it for 5 and subtract it.
Okay, so add multiples of 3 and 5, then subtract the doubly counted multiples of 50. How are you adding them? Is it 3 plus 6 is 9, plus 9 is 18, plus 12 is 30? Is this how you're doing it? This is how you add numbers, right?
Yeah.
Is there a better way to add the numbers?
Yes.
How?
If you find the largest multiple of 3 is 1,000, and you know what number multiple it is, you can just go 3 times and then
Yeah, I mean, it would be great if we had a formula for adding, right? Almost like some of this lecture might have even been prepared, right? So if we have a formula, I don't have to add them all. So a nice twist would be note 3 plus 6 plus 9 plus ... And I'll go to, 3 times m is just 3, 1 plus 2 plus ... plus m is 3 times m plus 1 over 2. So we could use something like that to make things a little bit easier. And now, if we do a formula like this, I could do a quadrillion without any trouble. So I'm no longer adding anything, I'm jumping to the final answer. This is very similar to the Binet formula. If we take a little bit of time and think, can I come up with a closed form expression? Now all of a sudden you just tell me what the number is and I just change the value, I evaluated that. There is one other way which is somewhat similar to this. You could do it in blocks of 30. It's really, I think, worse, to do it in blocks of 30 than to do it with multiples of 3, multiples of 5, and then subtract multiples of 15. But if we look at a block of 30, we could figure out what is the sum of the multiples of 3 and 5 in the block of 30. How would that change with the next block of 30? So if I looked at the first block of 30, what numbers would I have? Yes.
Oh, yeah, but here you're talking about 3, 6, 9, 12, 15, 18, 21.
Let's look carefully. We have 3, not 6.
I don't mean to start with 5. I thought I just should give you 5, I guess.
3 plus 5, plus 6, plus 9, plus 10. Yep.
Plus 12, plus 15.
Yep.
18, 20, 24, 25, 27. I think what we should do with this.
And so if I want 30, I might even start off with a 0 to do it like that.
And then I was thinking of like a similar approach. We could do like 1,000 divided by 30 to find like around like what number we have, like how many of these squares we need to have, and then the 30 times like all of these.
Yeah, so if this is the first block, how much more would the next block of 30 be?
Previous block plus this.
I think it'd be 2 times.
It'd be all like total amount of elements, so 14 times both block number times 30.
Good, so we've got to be a little bit careful because we're adding 30 to each one. So the next block equals the previous sum plus 30 times the number of elements. Right? So we could come up with a formula like this. And so if we do a little bit like this, we just have to be a little bit careful as we go from one block to the next, because we have to remember that we're putting in an additional 30 for each number. Which of these approaches would you like to code the most? Would you like to do number 3, where you code it for multiples of 3, multiples of 5, and then subtract off multiples of 15? Would you like to do one block of 30? In all of these, you also have to worry a little bit about if we don't quite end at a number that is a nice multiple of 3 and 5, we could have a partial block at the end. What's the best way to deal with a partial block? There's 2 possibilities.
Can you just brute force since it's going to be like a pretty small number?
You can. Which way do you want to brute force?
Well, I guess at the end, right? You try to subtract.
So do you subtract or do you add? So one possibility is you could stop a little bit before, because you have the incomplete block, and then add a bunch of terms. Or you could overshoot and then come down. It depends on how close you are as to do you want to overshoot or undershoot.
But
So for 990, I would say I would probably rather undershoot and add a little bit more. There are some things in trying to do matrix multiplication, efficiently or products efficiently, whatnot, where it's actually better to overshoot and then come back than to undershoot and add a bunch of things. And so we can talk about stuff like that later, but it's just something to keep in mind because there's this instinctive tendency to undershoot and then go up from that. It's sometimes better to overshoot and then correct. And so that's just a really good idea to put on your radar. So there's a lot of really good math behind a simple problem like this. Theoretically, adding multiples of numbers is trivial. But thinking about how can we do this efficiently, there's a lot of different approaches we can do. There's not one approach that it has to be done this way. What are the advantages and disadvantages? For the block approach, I think it's more work to do the block approach than to do 3. But again, it's a one-time calculation to set things up, and then which formula is going to be a little bit easier to use, which is going to be better in terms of overshooting and undershooting. If I'm doing things of block 30, that could have a little bit more exposure for overshooting and undershooting. But then it's only one thing that I have to worry about. Whereas for the 3s and the 5s and the 15s, I've got 3 different things maybe that I'm worrying about. So again, you want to keep in mind all these different concerns as to which one do you want to go with at the end of the day. Okay, the next is, I emailed you the link to the double plus and good using Fibonacci's for roulette. So just for completeness, I'm just including that in the slides. Okay, so I want to talk a little bit about going from recurrences to inequalities. Again, this is your dime. If people want, I'm happy to talk more about trying to do the recurrences for tiling. If not, I'm happy to talk about how would you prove things like Benet's formula, generating functions, how would you attack things like Catalan numbers. What are the preferences?
Compare results of tiling.
Okay, so do you guys have an answer for the tiling?
I wasn't really sure how to define T0. I kind of got stuck.
Okay, all right, so let's talk about the tiling. Is everybody either interested in tiling or able to look like they're interested? All right. So we talked about, we have this 3-dimensional problem now. And again, if I really cared about you, I would do a better job and just have some pictures, done in advance. And we'll look at it almost as like different levels. Oh, I should have brought the Legos from my office. And so one way of looking at things was as soon as we finish a level, we've reduced it to a previous problem. So we have the first segment up to the red line. And we have the next segment up to the blue line, then the next segment up to the green line, then the next segment up to the yellow line. And our tiles are 1 by 1 by 2. And Cn is the number of ways to tile the 2 by 2 by n. And so if we put down 2 tiles and completely tile the red section, then we reduced it to how many ways can we tile something of length n minus 1. How many ways are there to place 2 tiles to get the entire red section? 2 ways. They can both be parallel or both be vertical. And again, I apologize, the Legos are on the table in my office. So we know Cn would be 2 times Cn minus 1. Tile the red horizontally or vertically. Now, it's also possible that I could put down tiles and tile the red and the blue, because I can't just tile the red with my first 2 tiles. So I've got to have a tile coming in to red and blue. I could have all 4 tiles going in like that. And then how many ways would there be? So if I have the 4 tiles coming in, how many ways would there be from this point onward? So I've tiled the red and the blue levels. So how long is the object now at this point?
-2.
It would be Cn minus 2. So then I would have a plus 1 times Cn minus 2 tile red and blue by all 4 going inward. I like to explicitly put the 1 to remind myself where things are coming from. Now, what is the other possibility? I could have 2 coming in, and then the other one would have to be horizontal. Or I could have 2 coming in, and then 1 vertical. But do we agree that by symmetry, 2 coming in on the top and 1 horizontal on the bottom is the same as 2 coming in on the side and 1 up? I need to look at how many ways can I have 2 of the tiles coming in, but not all 4. If I had 3, there's no way to do it with just 3. And there's no way to do it with just 1. I've got to have at least 2. And exactly 2. How many ways can I choose 2 coming in and only 2 coming in? 4. So it's going to be plus 4 times, so number of ways just 2 going in. And then I have to have 1 on the bottom. And 1 on bottom. And now what we're going to do is we're going to introduce a new auxiliary sequence. And this is where my intuition was correct last time when I was talking about the Catalan numbers and how it was nice to split the problem to looking at not just how many ways are there to get from 0, 0 to nn, but how many ways are there conditioning on when I first hit the main line. Because I know I have to hit the main line at least once because I end there. This is an incredibly useful concept to sometimes know that something must happen. One of my favorite classes to teach is operations research. And the way you prove one of the biggest results is you have to show that there is a feasible solution that satisfies all the constraints. It doesn't matter how bad of a solution it is. You just need a starting solution, and then you can walk from that very quickly to an optimal solution. But you need a feasible solution. So imagine you own a movie theater, and I've actually done this in the industry. I've actually helped movie theaters with this. And you want to schedule movies, and you have a lot of constraints. Can somebody give me a constraint you might have if you own a movie theater?
Opening and closing time for the theater.
Opening and closing time. What else?
Number of movies you can show.
Number of movies you can show. How many movies can I show on a screen at a given time? Only 1. If you buy a copy of a movie, you can't show that movie on multiple screens at the same time. So there's a lot of constraints. Can you give me a schedule of showing movies that you know will satisfy all constraints? There's an obvious schedule that works. It's going to be really trivial if I'm telling you to do it without giving you any information. No movies. Show no movies. That will satisfy all the constraints. You won't have movies going past closing. You won't have movies starting before opening. You won't have multiple movies on the same screen. Show no movies. You own the airline. Can you give me a valid choice of flights? Fly no planes. Actually, this may not be just a hypothetical example. Okay, but for many things like that, you just need a starting point. And once you have that starting point, then you can move from it. And so when we were looking at the previous one, it's trying to find good ways to break things up. And so here, we are trying to find good ways to break things up. We're introducing auxiliary variables. We don't care about them at the end of the day. And so the question is, what do we want to call this? And so d n minus 1, it's going to look something like this, where I'm going to have two things like that, coming inward. And then underneath, if you can forgive the really bad drawing, maybe the red thing like that underneath. So it's kind of like an L, like a right angle. And so the distance from here to, whoops. So this distance over here would be n minus 1, because I've lost 1 unit over here, and I have 2 units over here. So maybe I'll call that dn minus 1. That's how many configurations there are that I can fill this up with, where I start up with 2 parallel horizontal pieces and then 1 piece underneath it. And so if I can figure out how many ways there are to complete that, then I can figure out how many ways there are to complete the original thing. So I now have this new relation for Cn. It's unfortunately not defined only in terms of Cn. It also involves Dn. So the question is, do I have a nice formula for Dn minus 1? So there are 2 things I could do. What are the 2 things I could do for the Dn minus 1? So somebody who wasn't in my office, what's the first natural way to try to continue to complete this? What could I do? Yeah, replicate the red block, and then that would fill it up, right? So we would get dn minus 1 would be, if I put in the 1 red block underneath it, now it's like the original problem, but what's the size? N minus 2. This is from a red block under. So does everyone see that if I just put a red block under, this is now going to be a complete 2 by 2 by 2? And now I just have something that has length n minus 2. The other possibility is, instead of putting the block so that I complete it, the block could stick out, which means its neighbor has to stick out, which means this now becomes the dn minus 2. Plus dn minus 2, 2 blocks on bottom stick out. Yes.
The case where we put replicate the red block, isn't that already counted? Except for 1 times C.
We're no, because they're not all in the same direction.
Is that second term to be C minus 2? Or is it C minus 1?
Oh, the second term should be Cn minus 2. Sorry, yes, thank you. That should be a Cn minus 2. So when you look at the 1 times Cn minus 2, that was where we put 4 blocks all coming straight in, going all the way marching down. All 4 of them were parallel to each other. And in this one, 2 are parallel, and then 1 is coming perpendicular to it. But again, for the other one, we're coming up with a relationship for dn minus 1. So we have, hopefully I can remember this as I go to the next page. We had Cn was 2 Cn minus 1 plus Cn minus 2 plus 4 dn minus 1. Is that right? And the other one we had dn minus 1 equaled Cn minus 2 plus dn minus 2. And we know C1 equaled 2 and C2 equals 9. And then the way we're defining our Ds, it's how many more spaces we have to complete. So what do you have for D1 and D2?
Okay, I probably did this wrong, but can you define C of 0 as 0?
You can define anything you want. The question is it a good definition? So C0 being 0 is not unreasonable.
Okay, because you can't like tie off something that doesn't exist, right?
So I am fine with provisionally setting C0 equals 0.
Yeah, and then.
What would you define D1 to be?
Well, I was going to define D1 based on the higher sequence if we assume that n equals 2.
Mm-hmm.
And then it's going to try like 9 equals 2 times.
But if we're going to define D, I think it's good to have a value of D1 or D2. So for D1, we would have our configuration where we want to put in just something of just one unit. I think D1 is just 1.
Is that based off of a visualization that D1 is actually?
I mean, D1 would be like this.
of
Would be
that-
like this
yeah,
configuration.
from a 2 by 2.
Is what we're saying. The subscript is telling us the length we need to go in the longest direction.
Right. Okay, that makes sense. So it's actually like a 2 by 2 by 2 situation.
So this might actually be a little bit degenerate. So in some sense, this might almost be like just having a block list above head. So I mean, to some extent, I don't actually care at this point that these two are parallel. If the two blues were in the same direction as the red, it would still have the same number of ways to complete it.
Right.
So I think so there's a lot of things where it doesn't matter how you got there, it just matters that you're there. And it doesn't matter that I got to this configuration by taking two blues that were parallel to each other. If people don't see this, please speak up. Do not look confused. Do not mentally hide the fact that you're confused. There are two ways to get to this configuration. I could take the two blues parallel to each other, going into the board, and then put a red underneath it. Or I could have the two blues in the same direction as the red, where one blue is directly on top of the red and the next blue is on top of it. It's physically going to be the same shape. You could. You could also have two vertical ones coming up and then something like that as well. That's another way to get to this configuration. There's lots of ways to get to this configuration. What I'm saying is when you're trying to count how many solutions there are, when you're trying to figure out what Cn is, it's enough to look at a configuration arising like this because we've handled the other cases.
We only care about the empty space.
We only care about the empty space. We don't care how we got to an L configuration with an empty space underneath. There's lots of ways I could have done this. I could have, as you said, I could have had two vertical and then a horizontal next to it. I could have two things coming in and one underneath it. Lots of different ways. But once I get to this configuration, I can change everything to the same color. I can heat it up so all the internal lines disappear. And then just ask how many ways are there to complete that? And so that's the different question. I'm not asking how many ways can I reach a shape like this. I'm saying once I have a shape like this, how many ways are there to complete it? And so I would say by calling this dn minus 1, we're saying the longest thing we need to complete has length n minus 1. So I would say d1 would mean I just have a horizontal bar above and an empty space below. There's one way to complete that. d2 would mean I would have to go 2 units further. How many ways can I complete 2 more things if I start off like that? So I could put both of them coming inward and then one on top, or I could put one horizontal. But if I put one horizontal, I then actually have 2 choices for the next one, both vertical. I think it's actually 3. I think D2 might be 3. So in what we had, we have something like this. Oops. With the red underneath going once. And so one possibility is I could put maybe like 2 greens coming in like this. Really bad. And then I would only have one thing that I could put up here. Or the other possibility, again with really crappy, and I should have brought the Legos, is I have my 2 blues, like this. I've got my red underneath, and then I put my green parallel to the red underneath. And now what's left over is just a C1 is how many ways can I cover 2 by 2 by 1.
I'm struggling to understand what shape this DM likes to have. So it would be an L shape where as of 2
No. The part that we always have is going to be extended one more. So if you want, I could even drop the initial part over here. I can really just view this as I have a block, a 1 by 1 by 2 block above. I don't really care about this first outer part anymore.
but how big is that empty space?
So the empty space, the length that I need to fill, that's the subscript. So if I say D5, I have 5 that I have to do on the bottom and 4 on the top. D6 would be 6 on the bottom and 5 on the top. So because we're coming from over here, we are coming from a situation where we filled 1 on the bottom, 1 on the top, and then 1 extra on the top. So that's why when we start off with something that was n units long, the new thing is n minus 1 units long. And that's why we're going to call it dn minus 1.
So you have 2 spaces to fill on the top and 1 on the bottom.
I would say the other way around. For this one, we have 1 fewer space on top than the bottom.
So there's 2 ways to do that.
So if you're looking at this one, it depends how long you want to go. So if we're doing D1, we've got 1 block on the top and an empty space on the bottom. There's only one way to do it. So D1 is 1. For D2, I've got to do 2 things on the bottom and 1 thing on the top. And one way to do that is if I put 2 things on the bottom going inward the same way, then I have to put 1 thing on top. There's only one way to do that. Or I could put something on the bottom to complete this and make this a 2 by 2 by 2. And then I've got now a 1 by 1 by 2 that I need to fill. And there's 2 ways to do that.
Oh, I see.
And so I should have brought the Legos. I do apologize. That's why I think it's C1. That's why I think D2 equals 3.
Okay, I see.
So I will start keeping just Legos. I'll just store Legos here for geometric problems. We'll hide them somewhere. So now we know what D1, D2, C1, C2 are. We can check and see if this is reasonable. How should we define D0?
Like I thought it should be 0 just because like you don't have anything that you can't file it anyway.
Right.
That's kind of like I'm not sure if that's the definition of like what D and N actually is.
So the question is, we may not be allowed to talk about that because this is talking about how you have a block on the top.
Yeah.
And so D0 may not be reasonable.
Also, I think if D0 exists, then it implies that there's C minus 1.
Right. And just, so I might actually say that we should not talk about D0. C0 is talking about how many ways are there to define to. Now, you might be able to extend, you can always extend these recurrences backwards. But sometimes they lose natural meaning. And if you extend them far enough backwards, you start getting negative numbers of ways of doing things. If people are interested, I can show you later in the semester that the -1/2 factorial is the square root of pi. The number of ways to arrange -1/2 of a person is the square root of pi. It's one of the most important facts in statistics.
Yeah.
Yes.
Where does it come up?
It comes from the gamma function, which is a generalization of the factorial function. So the factorial function is only defined initially for integers, but you can extend the definition of the factorial function to non-integers. You can extend it to negative numbers, to complex numbers. So we can talk about that later if people are interested. This does not mean that I can arrange -1/2 of a person. It means that the factorial function, which represents how many ways you can arrange n objects when n is an integer, has an extension and has a well-defined value for -1/2. But don't tell me that this is the same as arranging -1/2 of a person. So we could extend this sequence by using these recurrence values and put in negative indices and get numbers. But I no longer have the interpretation of something physical. So maybe we hold off on D0. So if we take n equals 3, that would give us D2 is going to be C1 plus D1. Does that make sense? Does that work? Is 3 equal to 1 plus 2? Yes. Right? So it's at least telling us that our notation is consistent. Now, if you wanted to try n equals 2, that would give you D1 equals C0 plus D0. What does D1 equal? 1. So that would mean 1 equals 0 plus D0.
Is that like mathematically valid?
Well, if you want to continue the sequence, it's telling you that the only way to do it is to say that D0 would have to be 1.
I guess you could interpret D0 as just having like one block on the top, but even though I'm not sure how to interpret it.
I'm not sure how to interpret it. You might interpret this as this one way to do nothing. But now what happens is you start going into negative values.
Kind of loses its meaning.
It loses its meaning. So now we have what almost looks like two equations and two unknowns. We have a recurrence relation involving C's. We have a recurrence relation involving D's. I can solve for C in terms of D, or I can solve for D in terms of C, and then substitute and create a new recurrence. What's nice is there's only two choices. Substitute D's for all the C's, substitute C's for all the D's. I would probably replace C's with D's, because I can easily solve for C in terms of the D's. But you could do it the other way, but then I would have to divide by 4, and that seems like more work. So I would probably say I can use this equation to get C n minus 2 is dn minus 1 plus, I'm sorry, minus, it's nice to erase, dn minus 2.
Or the move C, oh, the move 4 inside D.
I'm sorry?
You can move 4 inside D.
I could multiply through by 4.
I mean, as in physically moving the 4 in front of Cn minus 2. Inside D. That's,
The 4 in front of, the only 4 I have is the 4 dn minus 1.
yeah, like you remove the 4 there and you put it on the second line.
You'll multiply through by 4.
So 4 dn minus 1 equals 4.
Cn minus 2 plus 4 dn minus 2.
No, you don't have to. If you remove the 4, you only have to multiply the first term of your control.
But how do you remove the 4?
Just removing it. I think it works.
But I don't understand how you just remove it.
Well, the 4 means that the insides get multiplied, and you multiply the insides. So
Right.
you multiply the first term, and the second term is not necessary to multiply because it will be implied in it.
You can try writing it up and seeing if that works. I don't see right now.
It works for me.
Okay. I mean, it's probably just a way of doing a different way of doing the algebra. This allows me to replace C's in terms of the D's, and now I can take this and I can feed this into here, and then Cn becomes D n plus 1, I think. Yes. Minus dn, right? Equals 2 Cn minus 1, which would become D, I think n minus dn minus 1, I think, is just substitute in. Does everybody see that you can substitute in? All right, so if you have to leave, it's fine. So I have here Cn minus 2 is dn minus 1. Let's let m equal n minus 2. This gives you Cm. So that's the same as n equals m plus 2. So Cm is going to be d n minus 1. n minus 1 is going to be the same as m plus 1 minus dm. So wherever I have a cm, I can replace it with dm plus 1 minus dm. So I can take the first equation for cn, and I first take m equals n. Then I take m equals n minus 1. Then I take m equals n minus 2. And this will give me an equation for d. So this will give me a recurrence relation for d. So for the first one, that's where I'm going to get n plus 1 minus n. For the second one, if I take m equals n minus 1, I'll get n minus dn minus 1. The next term is cn minus 2, which would just be n minus 2, which just would be dn minus 1 minus dn minus 2. And then I'll have a plus 4 dn minus 1. So now I have a recurrence relation for d. And I can march down. And once I know the initial conditions, unfortunately, I need to know several initial conditions to use this. Right? It's not enough to just know the first two values, or is it? dn plus 1 is in terms of dn minus 1, and dn minus 2. I need 3 values. I need one more value of d if I want to march down. So your homework is think about, can you write like a Google Sheet or an Excel document to just march down and find these? You might have to calculate d3 by hand. Okay, that's not too bad. You can also get d3, that would be taking n equals 4, so we would need c2. Oh, we know what c2 is. So, again, if you have to leave, d3 should equal c, we're taking n equals 4, so that should be c2 plus d2. And c2 is 9, d2 is 3, so I think d3 is 12, and that should give you all that you need to march down.
Is there a nice way, like
There's a generalized Benet's formula that works for this, where I can write down the answer. It's going to involve the root of a cubic. So we'll do that on Monday. We'll finish solving this on Monday, because there's a lot of good math behind this. But the idea was this auxiliary variable was really nice. And what we're really doing, and I'll talk about this is almost like a Markov process where you have a bunch of different states. You have the state where everything is flush and complete. You have the state where something has an overhang. We're really lucky that we only have 2. We did a financial math, riddle problem where we were looking at sequences of coin tosses. And when you have something like that, if you want to know how often do you have, or how long do you have to wait on average before you see head, head, tail, head, that's much harder than head, 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 head. And you can just break it up into just going until you have something that repeats. So there's a lot of good stuff we can talk about. All right. Apologies for going over, but again, always feel free to just walk out.